comes in, pings an electron out off the atom, up into the conduction band. The electron's driven by an electric field down to this surface, or pulled to that surface by a positive charge on these capacitor plates. Every third capacitor plate has a negative charge and acts repulsively to confine the electron underneath the positively biased electrodes. Okay, so that's good. We've got a way of getting the photons in, of detecting them, of retaining them in place, avoiding the traps on the surface by doping this device. Now I've got to get the charge up. So if you observe this carefully, you see that every third electrode is connected to the same voltage. So there's actually only 3 control voltages going into the entire device, even though it might have millions of these or thousands of these electrodes. So what we can do is sequence the voltages on here so that we always have at least one positive and at least one negative, which means there's always one that's storing charge, one that's creating a barrier between the pixels, and one that's in transition between the two states.
Do you have to have conductive AR coating?
You don't have to. The reason you don't have to is because there's a zone of mobile carriers at the back surface that creates an extra equipotential here. But the devices that have very thick, and they put a high voltage on, do need to have the conductive coating on the back, and they use indium tin oxide for that, which tends to do bad things to the AR coating stack and hurts them a little bit in the UV. But they're the ones that are optimized for red sensitivity. They make them much thicker so that they can deal with the increasing absorption length in the red and extend the red response out there. So, here we go. This is how we sequence the electrodes. The charge is not mixing and it's traveling along, and out the other side. And so, one can transport an image from one side of the sheet of silicon to the other. And what we do is we set it up so that at the, I'm back into this electron micrograph. These are the columns running down here, and then out here you can see all of the bus structure for the electrodes, and if you look carefully you'll find out that there are 3 of these buses and they're connected to every third electrode going across the image area. And then there's a right angle bend. The columns empty into another sequence of electrodes that runs horizontally, and the charge ends up on this little thing here, which I have coloured. Oops, yes. The charge comes down the columns, gets clocked along the serial register and dumped onto the capacitors, this little strip of conductor there. We measure the charge, we reset it by activating the gate of this field effect transistor, which sucks the charge out and puts the voltage back to where it was. We measure it again, then we dump the charge, and then we measure it again. We take the difference of two values, one before and after the charge dump, then we reset the pixel. So what's happening is that we get a baseline value, we get a signal value, and because we're taking the difference, we're rejecting all of the noise power below the pixel frequency. And because we have a very low capacitance, we're getting quite a decent voltage out of the device. We're now able to make devices that are optimized well enough that we can get 1 electron RMS readout noise out of these devices, and we can get the well capacities, the pixel capacities, up to about 350,000. So that's a dynamic range of 350,000 to 1, which is really incredible for a device that's linear, has almost perfect charge transport, has almost 100% quantum efficiency. And the dark current record, I just got a paper from a guy at Fermilab who is reporting numbers down at the level of a few electrons, or photons, if you want to think of the equivalent optically, per day. So that's extremely hard to measure, of course. What they have to do is average over billions and billions of pixels to get an average rate that's at that level, and correct for all of the cosmic ray events which occur in the meantime, because these things detect particles and X-rays and all kinds of stuff as well. He's looking for low energy particles that might account for dark matter. and has a stack of these things down at the bottom of the mine in Batavia, outside of Chicago. It's kind of interesting. So, there we go. This is just in summary. We've got all of the CCD transfer registers, we dump the charge, we've got a reset transistor, buffer transistor to turn the voltage on the capacitor into something we can read. What do I mean by that? I mean that if you just connected this capacitor directly to the rest of the signal chain, you couldn't measure electron level signals, you'd suck the electron out instantly. So this field effect transistor has oxide isolated gate so that it reproduces the voltage on that capacitor on its output where it can drive a larger current. So it just basically buffers the voltage 1-to-1 but provides a low output impedance instead of the very high impedance of the capacitor. And then after that it's all just sampling, integration, noise filtering, digitization, and goes in the computer. How hard would that be? So, last section of this talk, just a quick spin through some of the surrounding logistics of making a camera with these ultra-sensitive detectors. This is an exploded view of the camera, and the sensors are over here, and they have flex cables that you saw on this sample here, coming to connectors out here. Those connectors plug into a printed circuit board there, whereas it's this one. At the back, and that printed circuit board is covered with preamplifiers. The traces travel on internal layers of the board. The board is trapped between two O-rings at the edge, so the signals can get from the vacuum side to the atmosphere side by travelling through internal layers of the board. And then there's a whole bunch of connectors along the edge of the board and cables that run up through the centre of the physical instrument. Anybody heard of them? Hexapod that Don Silverman has provided to us, and then the cables go along the spiders of the telescope to the outside world and the rest of the control electronics. So this thing is basically no bigger than the window, and the window is sized just big enough to accommodate the f2.5 beam expansion. So in fact the wall of the vacuum vessel is hiding under the edge of the beam. And there's no increase in the viewer beyond what's required optically. Here's a little schematic of our CCD down here with the field flattener lens on it. Now, you don't need to look at this. There's a huge amount of 3D modelling that goes into producing all these storyboards to put this thing together. It's like building a spacecraft. We get down in there in the clean room, we have these high-value, very, very delicate articles with all four edges exposed. You touch the edge, the device dies. So they've all got to be handled with, tools attaching to the back and with fixturing and alignment. And then we have to, so we make these storyboards, we go through, we review, then we have practice runs and rehearsals and so forth. I rewrote that storyboard so many times, I cannot tell you. I get down in the clean room and think, well, that's not so good, and we change the story as we went, which is probably not the way you're supposed to do it, but anyway. So, this is an example of some of the real hardware and fixturing. This is actually representative of the problem. The bond wires coming off the edge, this is the cable on the edge of the CCD. This is the silicon carbide CCD package. Here's the frame, the titanium frame I handed around, holding the Plano convex field flattener. And that little tang, that little tab of metal titanium sticking out there that's holding the lens, only has 500 microns of clearance to the top of the bond pipe pad. So if you get something misaligned during the assembly, you squish the bond pads and then you're very unhappy. But we got through the whole process. Here's a bin. There's one of these expensive CCDs, every one of these cells in this chamber here, after we've unified them with all of their lenses. And here we are raising the first one up into the focal plane using handling rods that are inserted from the back that went down and grabbed the back of the one that was in the bottom of the bin, and it's being drawn up into the focal plane. And so here it is installed, and lots of people in the clean room working away on it. And, this is just referencing the fact that there's all sorts of refrigeration systems involved in this because it runs at 165 Kelvin. So, Optical Society will be interested in a piece of fused silica. This is the meniscus window, has polished edges because we're worried about fracture propagation. This thing is supporting 2.3 tonnes of atmospheric force. It's 32 millimetres thick in the centre. Factor of safety of 7. We really sweated that. We were really worried that that thing would fail on us and we would lose the whole focal plane. In the end, it turned out to be a beautiful piece of glass. These gentlemen here are looking through half a metre of fused silica edge on from the other side of the optic. So, just quickly, the problem with this optical design, I'm not going to show you spot diagrams and ray tracing or anything like that, but the problem is that Bernhard Schmidt, who came up with the Schmidt telescope, had a simple idea for making a wide field camera, which was to use a spherical mirror that looks the same from every direction. Now, the problem, of course, is you get a huge amount of spherical aberration from a spherical mirror, so he devised a scheme to build a fourth order aspheric corrector at the pupil, which is placed at the centre of the radius of curvature of the primary. And this is great. It produces nice images with a spherical focal surface. The problem is that our sensors are no longer a photographic film, which is what he had in mind. He would curve the photographic plate into a spherical shape using a vacuum chuck assembly. And that's how this telescope worked for the first part of its life. But when you put a silicon sensor in there, the silicon has to be operated at low temperature to avoid a lot of dark current. That's the thermally generated electrons. You can get electrons promoted from the valence to the conduction band just by the vibrational energy in the crystal lattice. And to get rid of that, you cool it. But if you cool it, it has to be in a vacuum. If it has to be in a vacuum, it has to have a window. And the window is fine. It can be used as a field flattener. Except when you make the focal plane above a certain size, the central thickness of the field flattener gets to a point that the change in refractive index, the dispersion of the glass is getting you, and you can't focus the image across the entire width of your broadband filter. So to address that, we went back to the curved focal surface, the CCDs on the cords. We took out some of the power in the window. And basically, the problem we were left with was that we still needed to make the window a certain thickness so that it would not collapse under atmospheric pressure. And it was a very, very delicate trade with lots of FEA to figure out how to control the stress without killing the optical performance of the system. Anyway, we made it in the end. The window didn't break, and here's a picture of the system assembled with the window in place and under vacuum and all of the CCDs installed. It's being suspended on a crane, and I'll take a photograph from underneath. This instrument will never ever look upwards because I don't want any of the particles rattling around in the system to get onto the sensors. There are not supposed to be any particles inside the viewer, of course. We're in the clean room, but you know, nothing's ever perfect. Now, a big window like that has a problem that it's facing a 165 Kelvin focal plane and transferring 30 watts through radiative cooling into the interior. The equilibrium temperature of the glass is going to end up being at about minus 20 degrees C, which is obviously bad for frosting and condensation. So, gentlemen over here, transparent coating. We put indium tin oxide in the anti-reflection layer stack, and that thing there is a conductive gasket, and another one down there, and we put 66 volts across it and replace the entire power loss to the interior with heating on the interior surface. It costs us about 2% in throughput because of the absorption in the coating. It's, by the way, it's not normally at 28 degrees, it's just that we didn't have the CCD's refrigerator turned on when we ran this test. The image on the left is actually showing the equilibration of the system with the CCDs cold and the centre of the window being actively returned to room temperature. I was pretty pleased about that. So anyway, there's a reminder of what the cutaway view of the telescope looks like. I've talked at great length about the camera and the viewer. In front of this, there's a filter, and that's kind of interesting. And up here is a shutter. The reason that the shutter has to be at the top end of the telescope on a Schmidt is that when you open the shutter blades, they're going to be in the beam, and they're going to obstruct the light that's passing your prime focus. And so the only place you can actually open the shutter is to take the blades all the way out to the edge of the telescope. So the specialists in building large astronomical shutters freaked out when I went to them and said, the specs for this shutter are that it has to have 1.2 metre aperture, and you need to open and close in half a second each. And you're not allowed to vibrate my telescope. I need no more than 0.1 arc-second disturbance of my pointing when you do it. And so they told me it couldn't be done. I told them, well, okay, I'll do it then. And they said, all right, I give up, we'll do it. And so what we did was they made a belt drive with the blade. Oh, here we go, we've got a picture. One blade attached, these are the two blades. They're painted white on the interior. This is the shutter. It runs from here up to here. It's the size of a table tennis table. The blades are painted white on the inside, so we can use the interior as a calibration screen during the daytime by illuminating the interior of the shutter. But the two blades are just flat honeycomb plates. One attaches to one side of the belt, and the other to the other side of the belt. The masses are matched, and there's a servo motor with a velocity profile that minimises the vibration. And it works really well, and it's working really well tonight because we're testing it on the camera that we have in place for the next couple of months just to check out its reliability. Okay, last thing. Last novel thing is that the filter exchanger is an industrial robot arm, and it presents the filters to the front of the instrument here. There's a redundant latching system. There are electropermanent magnets, which are permanent magnets that are basically solenoids with permanent magnets in their core. You activate them to release the magnet rather than to activate the magnet. They're active when they're powered off. And they hold the filter frame up against the front of the instrument. $100,000 filter dropped on $1 million primary mirror is an unhappy event. So we actually have a very clever secondary latching mechanism where there are some pins that stick out and are trapped the entire time either in one side of the latch or the other. This particular secondary latch, actually there's no contact between any of the parts. It's just there in case the magnets let go. So there's a computer that's sequencing all of these latches and sensors that read whether they're working or not. We measure the inductance of the solenoids to know whether the magnets are latched. And the arm picks the filter up and shoves it in a box down here. Box down there. That actually is the access manhole for the telescope, and this hole up here is the original photographic plate loading hole. The robot shoves the filter in the box, the same set of latches retain the filter there, sticks its finger in and grabs the next filter, puts it on the instrument, and then does this, and puts its arm against the wall of the telescope to get the arm under this ring girder and out of the way of the beam. So that's kind of like unheard of, almost unheard of filter exchange mechanism. These are my, young engineering team. They all look really young to me, except this guy. I think Michael's doing his PhD, isn't he? Michael?
A master's at UCLA.
And this young man's a high school student who did all of the magnetic latch characterization. And at the end of the summer, I didn't realise, I was just chatting with one of my colleagues, he said, oh, Zimmer, do you know any other Zimmers? Jake? No. Like Hans Zimmer is his dad? Oh, wow, he's like the most famous movie soundtrack writer around here. So anyway, he never mentioned that to me. Okay, so there we go. So how do we do this? 1,000 times faster was my claim. Actually, in the flyer I said 1,500, but I hadn't taken into account the clear weather fraction. I was counting every night as clear. So I'm adjusting that downwards to 1,000. Still pretty good. We have about 30% more field of view with our CCD camera. And we managed to take 1,030 images a night instead of 1.5. And we get there by having about 100 times the sensitivity of photographic plates and automating the whole process. So There's no delay time to repoint the telescope manually. It's all done by computer control. It takes 10 seconds. We get the data out of the camera in the same 10 seconds. It gets relayed over a microwave link down to the San Diego Supercomputing Center and then relayed to Caltech from there, all across the network automatically. The images are ingested, processed, and there is identification of targets within about 30 seconds. So this system doesn't get tired, it doesn't need to go to the bathroom, it doesn't get sick, it works all night. Donald Trump would be most unhappy. So we put a lot of people out of work, right? So it's just much, much more efficient. They only averaged about 1.5 photographic plates a night when they did the original survey. They took 7 years to get the first 99% of the plates, and we do that much in less than a night. And we're better. We have continuous image quality monitoring, focus. We measure the Zernicke coefficients of the wavefront by looking at extrafocal images. We monitor the atmospheric extinction variations, that's the transmission of the atmosphere. We can see track rate with our guiders, wind shake. The sensors have fundamentally more linearity, dynamic range. They're better calibrated. The image analysis is automatic, as I mentioned. And not only that, but we use the internet to notify telescopes all around the world to do follow-up spectroscopy. And that, of course, is very much the power of the whole thing. I've already mentioned Fritz Zwicky and his many accomplishments. But I want to come back to where I started at the beginning of the talk. I said it was amazing working around here with all the people and all the history and this sense that you're there where it's happening. You know, you're meeting these people all the time. So I was chatting over dinner about my long-running house renovation project, and in the very early days of that, I went to an interview with a design build company where they had a little sandwich and presentation and so forth, and people had name tags on. And there was a woman there, and her name said Barbara Zwicky. And I said, "Wow, you have such an unusual surname." I said, "Did you know that there was a really famous Caltech astronomer who had the same last name? Did you ever know about that?" And she said, "Yeah, he was my dad." She's younger than me, so Fritz was, actually I figured out that she was born, I think he died when she was about 4 or 5 years old. I don't think she really actually knew him. I didn't, of course, get into that when I was talking to her, but when I was reading about this, I realised that he was well on in life when she was born. All right, so I think that's more than enough. Just take any questions while if you have any. This is just a little simulation of the rather crazy ideas that the astronomers have for in what order to survey the sky. It's not as simple as you might think, because one guy wants to do whole sky coverage all in one colour every night, and someone else wants to visit the same spot on the sky every hour because they're interested in objects that have different event lifetimes and things like that. And so it's done in multiple colours. And anyway, not my problem, that part of it. So there we go. We're onwards to the next adventure. So thank you very much.
Which Schmidt telescope was this on Palomar?
This is the 48-inch Schmidt on Palomar.
Is that the Ocean?
The Ocean Schmidt, yes. It's now known as the Ocean Schmidt telescope, absolutely. And it's the telescope that was used to do the original photographic survey. And if you want to see the original photographic survey, just download Google Earth and hit the Google Sky button, and that's the Palomar Digital Sky Survey on Google.
When you were showing one of the early slides of the galaxy, we were seeing a lot of colored universes, I guess. Was there any false coloring there? Were the colors saturated or exaggerated?
You know, I'm I'm going to bring my laptop over for you to have a look at because the false colour is coming out of your projector. No. Well, yes and no. Any astronomical image is made with a set of, spectral band passes, and rarely are those spectral band passes aligned to the much more limited colour range that your eye sees, and so there's always some artistic judgment required as to how to represent what these objects would really look like if they were bright enough for your eye to see the colour. If you look through a telescope at an astronomical object, it looks black and white. You don't see any colour because they're not bright enough for your eye's colour sensors to register. You only get, is it the rods or the cones? Can somebody help me out? It's you're only seeing intensity. So all of these images only have visible colour when you photograph them.
So some of those might have been in your IR or perhaps some of
Yeah.
your UV, and they were so
People tend to, they tend to put oxygen, which is approximately green, as a green, but which green do they pick on their monitor? They pick what looks nice. Hydrogen, is it red or is it purpley colour? It's just, depends. On all the photographic images where they did actually use colour printing methods to represent the colour, they tend to always represent them as sort of purple. But I don't think that's real. Yeah. I would like people to see a couple of those images that didn't really reproduce very well, so I'll just leave them up on my laptop if you want to just cruise by. The ones of the night sky with the Milky Way are well, it was fun to take the picture. I got asked by the astronomer who was working at the time, could I please get off the mountain? Because what happened was that when I took the pictures, word got out, and there are 6 or 8 telescopes, each of which have a telescope operator, and everybody ran outside to have their picture taken. They were so excited about the pictures. I had actually set the camera up. I'd taken one of the viewers, one of the cryostats, off one of the telescopes, and had made an adapter to bolt a Hasselblad wide-angle lens on the front with a Uni-Blitz electromagnetic shutter. And so I built sort of my own homemade camera, and because I just had a liquid nitrogen-filled cylinder, a Dewar, I put it in the dirt, resting on its electronics box that was sitting out the side and pivoting, and then used a scissor jack, a lab jack, to get the tilt right, and just dragged it around the dirt and had a fibre optic cable running to one of the computers in the nearby dome. So it was ultra crude, the whole setup, and so I had this thing, this very, very expensive piece of equipment just sitting out in the dirt out there. And when I took the picture, somebody saw it on a monitor, and they all came out saying, "Oh wow, this is great." It sort of went viral. The word went viral. It wasn't actually invented yet, but it was fun. But the image illustrates that what you would see. This is not your colour question, but this is what you would see if your eyes were more sensitive and you just turned up the game. Okay, this is what the sky actually looks like, and people look at that and say, "Nah, you're kidding." Oh, wow. Yeah, right. So there's quite a lot of stuff there. Let me see if I can make it bigger.
Not starlight.
Yeah.
Galaxy light.
Yeah, and
Stardust light.
so the dark areas here are dust obscuring the edge of our seen edge on in our galaxy. So the dark areas are not lack of stars, they're excess of dust. And you can hardly see any of the constellations because they're not, the bright stars don't look a lot brighter than all the faint stars because of the dynamic range of the display. That's actually the Southern Cross. You can see there's 4 stars down here. And these 2 cloudy things here are the Magellanic Clouds, named that way by Magellan, because when he came down to the southern hemisphere, when he was circumnavigating the globe, He was the first European to report those objects, and those are the galaxies that are the nearest to our own.